Thanks. Thanks, James, for the introduction. None of my SAMS questions involve any mental arithmetic, so giving you that warning up front. Okay, wrong direction. Oh, the big green button. Okay, so a couple of disclosures. Learning objectives of this talk: provide an overview of Linac-based SRS SBRT capabilities, plus an overview of imaging capabilities and motion management capabilities. I should apologize up front. The Henry Ford experience is with Varian and the Edge, but the intention is not to be vendor specific here. All the equipment suppliers of delivery platforms are here at the workshop, so please feel free, particularly tomorrow, to map the types of capabilities I'm talking about in relation to the Edge to the other systems you're interested in. So the Edge platform that has been up and running at Henry Ford for about a year now, a little bit over a year. This is the summary of the system. We originally obtained the Edge with 6x and 10x flattening filter-free modes, but we added a 6x flattened mode to give it a little bit more flexibility. It has 2.5 MV imaging mode, energy, and the high definition 120 MLC. It has the newer MV detector on the Varian machines, which is not the AS1000, it's the AS1200 here, otherwise known as the digital megavoltage imager, which has 43 centimeters squared panel and a bit of higher resolution. Also on the Edge, part of the Varian package is the Perfect Pitch 60 couch, which you see there at the top right. In terms of imaging capabilities, we have the onboard imager, the MV imager. There's an optical surface monitoring system, the OSMS, which has a number of cameras on the ceiling mounted cameras, and the Calypso system, which most people will be familiar with. So just to give a brief overview of how we've used the Edge since acquiring it, these are the kinds of cases we've treated. This is dated by a few months now, but gives you a picture. A lot of brain cranial, and as you heard from Dr. Siddiqui and Winston earlier, spine and lung, and then a smaller number of cases in these other categories. So the goal of this talk was to review features relevant, Linac-based features relevant to SRS and SBRT. So these are the features I wanted to walk through. Isocenter accuracy, flattening filter-free beams, which potentially offer sharper penumbra and high dose rate. The collimation modes, HDMLC or the cones. The range of delivery techniques, a lot of which have been discussed already. IMRT, VMAT, dynamic conformal arc. The single ISO multi-target is a combination that's been discussed, but it'll use either dynamic conformal arc or VMAT. The Perfect Pitch 60 couch, thermoplastic, the immobilization devices we're using, and importantly, the advanced imaging and some of the other options, the OSMS and Calypso. So just as a heads up to folks, when Henry Ford acquired its Novalis TX a few years back, it produced a paper on commissioning of that, and there's a parallel paper on commissioning of the Edge system, so it's always good if you're commissioning one of your own to compare with what other people have done, look at their data. So this paper came out not too long ago. First author, Winston Wen, who spoke earlier, and that gives a bunch of potentially useful data if you're doing your own commissioning. We actually went through a fair bit of additional work beyond what was immediately needed for the Edge. We tried 6 detectors for the small field dosimetry, commissioned 5 different treatment planning systems, including an in-house Monte Carlo system, etc. Not all of that is mentioned in the paper, but a lot of good stuff in terms of PDDs, profiles, output factors is reported so you can compare. Otherwise notable, we briefly discuss sort of the end-to-end commissioning and the comparison of IMRT, rapid arc cases, TG119, etc. So in terms of mechanical accuracy, you have a number of capabilities with the newer systems that help you maintain very tight mechanical specs. So at the time of commissioning, Winston was leading that and pushed the Varian installers to achieve pretty tight, what we thought was pretty tight specs for the accuracy. So as you see here, After gantry, collimator, and couch are finally all accounted for, we were within, we're at 0.44 millimeters, which we were pleased with. Now, there are some nice tools that help you maintain that accuracy as you use the system to treat. So one of those is the IsoCal system that is designed to bring the sort of technology that's used for isolock into the clinic so that the physics team can use it. It measures the isocenter position accurately using multiple gantry angles, and then measures the isocenter positions for the MV and KV images and writes an XML file to disk so that the system uses it to correct after each calibration, if you like, where the true isocenter of the imaging systems is, so that it's well aligned with the mechanical radiation isocenter. So a valuable tool, and one that you would be recommended to get with your system. On a day-to-day basis, there's a machine performance check package, which I believe comes standard now with TrueBeam and the Edge system, but that'd be something to verify with Varian if you're considering buying a Varian machine. This gives you, our therapists actually run this, and it's checked by physicists daily, and it will report on the mechanical specs as well as the imager offsets, and we expect to see all those at within the tolerances matching commissioning numbers. So we didn't trust these systems, of course. We did our own verifications. So there's some kind of busy plots that I got from Winston, but they show that we use the IsoCal system to measure the offset of the center of jaw-defined, MLC-defined, and cone-defined and cone-defined fields from the nominal isocenter position, and over different gantry and couch rotation angles, and using either auto registration that's built into IsoCal or auto with manual corrections, and basically verified that the numbers we get out of this exercise closely match what we get out of the machine performance check software. So the end result is that we had it commissioning and continue to maintain pretty tight specs on this particular delivery platform. So max isocenter deviation accounted for gantry, collimator, and couch is less than 0.9 millimeter, with the standard deviation around about 0.3. So in case you're interested in comparing during as you go into your own commissioning, I thought I'd report those figures. So getting on to the flattening filter-free, the benefits of flattening filter-free modes in particular. So sometimes it's claimed that the penumbra there is sharper, and that's a benefit. In fact, I quoted a paper here that shows it's not particularly different. What you will get a benefit from the flattening filter-free fields is the higher dose rates. So at least on the Varian machines, the 6X goes up to 1400 MUs per minute and the 18X to 24. So clearly a great benefit for faster deliveries and to reduce the impact of patient motion, since the patient's on the couch a lot less or for a shorter time, and more efficient use of breath hold and gating. So the HDMLC collimator now, and this will help you out with a Sam's question. Has central leaf width of 2.5, and Winston discussed the trade-offs there a bit earlier, and particularly for smaller targets, you get a benefit in the conformity index from the 2.5 millimeter central leaf width. During commissioning, we adjusted the dynamic leaf gap iteratively to give best agreement between calculation and measurement for 3 spine plans. And you have a bit of a trade-off there whether you want to adjust that to give best match for larger targets or smaller. So because this was a machine that was largely used for SRS SBRT, we opted to optimize for smaller targets there. Eclipse notably only allows 1 dynamic leaf cap value per beam model. Other treatment planning systems might allow more flexibility, so in that case you can probably optimize further. But just to mention that limitation. There's this nice presentation on the web from the Palo Alto Medical Foundation guys. They point out that you have the 2.5 millimeter inner leaves, and also on this particular HDMLC, they have increased the radius, the diameter of the rounded leaf tips to provide a sharper penumbra. So that's at 16 cm compared to 8 for the Millennium. So, first Sam's question. On the Varian HDMLC, the isocenter plane inner leaf width and leaf end radius of curvature are 1, 0.5 cm, 5 millimeters, 16 cm, 2.5 millimeters, 4 cm, 0.03 centimeters, and 8 cm. Excuse me, fighting a cold. 2.5 millimeters and 16 cm, and 2.5 millimeters and 10 angstroms. Great, so the 73% got the right answer at 2.5 millimeter inner leaf width and the 16 cm diameter, which was on the previous slide. And there's a couple of references there to give you more detail on the physical characteristics of the HDMLC. Okay, cones. We have cones that range in size from 4 millimeter up to 17.5 millimeter. With cones, you're interested in obtaining the TMRs, and they can be obtained by two methods, the PDD conversion, so measure the PDDs and convert using the Batum method, or via direct measurement, in which case you're wrestling with your 3D scanning system to make sure it has the capability to raise and lower the water depth, etc. Just here I've included the Batum paper and the traditional TMR relationship for converting PDDs to TMR. Here it becomes a little bit more complex in that case. The Batum conversion method is a modeling method, so it has some inherent uncertainties in it. In general, measuring any of this small field dosimetry is very challenging. One of our folks, Hyson Lee, who's here today, did a lot of excellent work on this and a lot of detailed measurements reported at the 2015 annual meeting. The bottom line here is he looked at both the case of direct measurements and also the conversion using the Batum method. And this slide is kind of busy, so I don't try to take in all the detail here. The bottom line here is that in measuring PDDs, you have to be very careful to get on the central axis of the beam, which isn't always easy, because even a slight angular measurement, a slight angular deviation will throw you out. So the bottom right panel here indicates one of his results is that errors in the PDD, errors in measured PDDs will introduce errors into TMRs of up to about 5%, unless you're very careful to get the measurements taken exactly along the central axis of the beam. And one method of doing that he found useful was to use we're using the sun nuclear scanner, so he used this feature, the ray trace feature, I believe it's called, to exactly get the central axis aligned with your measurement, your scanning direction. So I thought I'd mention that as a practical thing to understand when you're doing your commissioning measurements. So next Sam's question. Obtaining TMRs for cone commissioning is difficult for all of the following reasons except PDD to TMR conversion equations suffer from uncertainties. Scanning tank TMR feature does not always work well. TMRs are sensitive to temperature and pressure correction uncertainties. It's difficult to align PDD scans with the central axis. Small field dosimetry is challenging and requires careful selection of the detectors. So which of those is incorrect? Excellent. That is the correct answer. All those other factors do complicate the acquisition of TMRs or the conversion of PDDs to TMRs. The one thing that doesn't apply is that PDD and TMR measurements are no more sensitive to temperature and pressure corrections than any other measurements. Okay, in terms of delivery techniques, and these were discussed in good detail. We heard a lot about these earlier, a lot of valuable information. So the Linac-based delivery offers the options of IMRT, of course, and VMAT. which I think most people would be familiar with. Dynamic conformal arc is a good tried and true standby method for a lot of techniques. I wanted to point out that in iPlan, which we have used in the past and continue to use, the MLC reshapes every 10 degrees. In Eclipse, you can choose the angular frequency at which you reshape the aperture. So that's something that our team is still starting to work out what the best trade-off is there. In the single isocenter multi-target type approach, we, as Winston indicated, we treat fewer than 5, or I think he said 6, so it's 5 to 6. No more than that. And we place distance limits due to concerns about residual geometric uncertainties. So I'm quoting a paper by Winston out of TCRT here. And this is, I omitted the scales on this, but I think the time scale would be minutes, and the length scales would be millimeters, and the degree scale, the angle scales would be degrees. But basically what you see is the translational uncertainties are kind of have some kind of systematic component and then a random component that doesn't change too much with time. But you can expect pitch and roll and yaw deviations to increase as you increase the length of time that a patient stays on the couch. So that becomes a concern and something that you want to be aware of when you're using different treatment techniques. So the perfect pitch 60 couch is shown here. Just a few points about that. The perfect pitch couch reintroduced movable rails, which are not indexed, which have significant attenuation, requiring a couch model in the treatment planning system. And that couch model is available as a standard feature in ARIA version 13, but not earlier versions, so we built our own in that case. So that's something you want to take into account. And then, of course, you have to pay attention for different treatment techniques. So if you're treating spine, for example, previously, before we went to the edge, we didn't have to worry too much. We didn't have to worry all about rail position, just attenuation through a flat couch top. Now we have to take care, and the therapists have to take care that the rails are moved out of the way of the beam, so you're not, none of the beams is entering through the movable rails. So one complication with this. QFix has a number of couch inserts with this couch top, including a Calypso compatible insert that reduces the impact on the electromagnetic tracking, but has a slightly higher attenuation. So we had to make a number of changes to, nothing huge, but a number of changes to our treatment planning approaches to accommodate this. So in terms of mobilization devices, thermoplastic mask is used for the bulk of cranial cases. And what you see here is a mask with a face cutout to accommodate the optical surface monitoring system for cranial treatments. So the optical surface monitoring system is looking at the exposed part of the patient's face and using the cheekbones, etc., to monitor motion in 6D. So I'll have another slide on that shortly. There is the head frame, which we'll use for certain functional treatments. And for SBR treatments, we're using the blue bag with or without that plastic wrap to suppress or reduce the breathing motion somewhat. So the TrueBeam 2.0, but we're starting to move to TrueBeam 2.5 package now. So the Edge is essentially a TrueBeam platform with sort of a package of features designed to treat SRS and SBRT. So it runs on TrueBeam software. So the TrueBeam 2.0 imaging package consisted of the following components. In terms of KV imaging, there's 40 CBCT, which is new, but though you can acquire a 40 CBCT at the time you treat the patient, it can be reconstructed and viewed offline. It can't be used online. There's a number of options for triggered imaging, and I'll show you more of those. On-demand imaging, which doesn't have to be pre-configured. You can interrupt the treatment at any point and use one of the on-demand imaging options to verify patient setup. 2D, 3D registration now instead of the previous 2D, 2D registration, which we found very helpful. And then extended CBCTs, where you can extend the field of view on a CBCT by taking multiple shifted CBCTs and have the system stitch them together for you. In terms of MV imaging, I mentioned there's the 2.5 MV flattening filter-free energy for imaging. So a little bit better for larger patients. The Cine mode also for MV imaging, which of course was there before, but continues to be an option. The optical surface monitoring system, which I've mentioned, and Calypso. So just a little bit more detail on these various options. The Edge TrueBeam onboard imager properties are as follows. I'll let you read some of these and try and pick out the highlights. CBCTs can be acquired at slow to fast rotations. So we use, for example, 3 degrees per second down to 1 degree per second, depending on how much, the quality of the image you want and the structures you're trying to see. And fluoroscopic imaging options continue to be there. The MV imager properties, it's the new digital megavoltage imager. It has increased build-up to hopefully reduce the impact of scatter on the image, make that more uniform. It's got a larger 43 cm squared panel and supports high dose rate beams. 40 CBCTs I mentioned. The experience at Henry Ford is that these are subject to streaking artifacts, so we're using those at the moment for peripheral lung only. Extended CBCTs, you can stitch together any number of shifted CBCTs, reconstruct offline. As mentioned previously, no ability to use at this point for online setup. On-demand imaging, you can use only if pitch and roll is 0, so you've got to be aware of in-room clearance and so on. But I'll come to that. I have a few more slides on that. And triggered KV-MV imaging triggers on MU as you're delivering some interval, MU interval as you're delivering the treatment, or the gantry angle or time, and I'll give you a bit more information on that shortly. The OSMS, again, optical surface monitoring system from 3 cameras, which separately are monitoring the surface of the patient and determining, quantifying the patient position in 6D, and you can select the field of view that you want the system to use, or the part of the patient surface that you want it to use for determining position. And then Calypso, which is now approved for any soft tissue site where markers have been used, although use for the lung is still pending, I believe. So in terms of on-demand imaging, here's the kind of thing you would see at the console. You're just adding the imaging on an ad hoc basis because you want to, for example, you're concerned the patient might have shifted, or you want to verify setup, etc. So we use this, for example, in SRS treatments with couch kicks to check the patient setup at each new couch angle before beaming on. So flexible and useful capability that's added in this latest version of TrueBeam software. Triggered imaging is imaging that you can configure during treatment and acquire KV images at specific intervals of either MU or gantry angle or time. And I believe these are the minimum values, so you can take images that are down to about 3 seconds intervals, but not below. Gantry angles are 10 degrees and time, for example, 3 seconds. So the planning contours, for example, the PTV can be overlaid on the KV image with some limitations, and the beam can be manually stopped when needed if you have sufficient image quality already. Useful for intrafraction tracking, for example, in spine radiosurgery, and available on any delivery technique. So here's an example of triggered imaging. One of the current limitations, at least in TrueBeam 2.0, and I'm not sure whether it's been fixed in 2.5 or will be fixed in future, but the DRR is available only on the first treatment gantry angle. So at the console, the DRR becomes of limited use if you're away from that first treatment gantry angle. Nevertheless, you can superimpose structures such as the PTV on your images, which you kind of see here, to provide some assurance that you're treating the right target and still, patient's still aligned. So auto beam hold is another feature that's useful to be aware of. So there's going to be a Sam's question on this. Auto beam hold is a triggered imaging application with automatic marker detection and automatic beam hold. It beams on only when the markers are within an allowed radius. And it also allows manual as well as automatic control by operators. So if the therapists want to, they can disable the automatic beam hold and manually beam on when they see the markers go within the target area. So this becomes a bit clearer. This is how you would set it up at the console. You've got a number of options to choose. The frequency with which these images are taken, so I think the minimum interval is 3 seconds. You can specify a search region, and I'm not sure of what the options there should be. You can specify a marker detection method which might be optimized for a particular type of implanted marker you're using, so gold seed is highlighted here, for example. And then you can specify the kind of regions that you want to keep the markers within. So this is an example of how we commission the system. Shows it pretty clearly. We've got a moving stage here where this phantom with several implanted BBs is moving in the supinf direction. And we've indicated these green circles as the regions we want the markers that are detected by the auto beam hold software to stay within. So as long as all the markers are within those circles, the beam stays on. When one or more of them moves outside, which you see on the panel at the top far right, two of the circles have gone red because the detected markers have moved outside your tolerance radius there, the beam's held off. So this system, we haven't used this frequently, but we've used it for certain challenging cases in the abdomen where there was a lot of abdominal, gas going through, and the abdominal structures were moving around as a result. This was an SBRT treatment, I believe, and in this case, we contoured at the treatment planning, contoured the implanted fiducials, specified, used the 4D CT to construct an ITV and a PTV around each of those implanted fiducials. And then at the time of treatment, the therapists were using this capabilities, auto beam hold capability, and manually beaming on when they could see all the fiducials within the ITV, and beaming off when they moved outside. So in this case, it worked very well, actually, and delivered a treatment to the patient which wouldn't have been easily achievable using other methods. So, final Sam's question on auto beam hold. Which statement is wrong? The auto beam hold capability is a triggered imaging capability, includes user configurable search region where the beam's turned on, enables automatic beam hold, permits manual beam hold by therapists, and automatically detects the tumor. Correct. Auto beam hold's designed to detect implanted fiducials, not the tumor. It's not that sophisticated or ambitious. So, and you can find some details about that in this Varian auto beam hold quick tip document. So finally, the OSMS, which is being discussed in some of the previous presentations, and consists of 3 cameras on the ceiling which beam light onto the patient's surface, and then that light is reflected back, and the cameras sense that, build up a pixelated version of this patient's surface. They're using as reference the patient surface they've acquired from the planning CT, and although you can re-specify the reference image at the time of the first fraction, for example. So here's an example of the display you get. In this case, the patient's region around the eyes and nose has been blocked out by the therapist as the region of interest that OSMS would use, and you can specify thresholds within which the vertical, longitudinal, latitudinal, magnitude, rotation, roll, and pitch need to stay in order for the beam to stay on. If those thresholds are exceeded, then the beam is held. So, in summary, the expectations for a Linac-based SRS SBRT platform are to maintain tight mechanical isocenter accuracy, exploit the flattening filter-free beams and collimators to provide conformal dose sharp fall-off, exploit the range of delivery techniques that you have available to you with the treatment planning systems. You need to choose appropriate immobilization devices and understand the residual uncertainties associated with those, and exploit the advanced imaging capabilities in particular, not only to set up the patient, but to monitor residual motion and understand your geometric uncertainties. And some thanks to all the people who contributed material. Thank you.